Tell me if the audio coming through there. There's going to be a sad live stream because I get the paper here and we're just going to go through some answers. Whether or not you want to stay, that's up to you. Free will. If you want to watch it after, it's up to you. If you just want to wait, for your your results, that's up to you. If you don't want to go for the results and you just want to kick back and relax, that is up to you. But whoever wants it, you can send it to anybody. I can start in 2 minutes. We have some people saying the thing was easy. But if the thing was hard, I'll say we're going through the paper ones. Alright. Let me know if audio and video coming through clearly. But it's big we're going through on Sunday though. All right. We get started here. I say expecting like 5 people to come this thing. Alright, so the first thing here is state Hooke's law. There's 3 marks, right? But what you want to state, I mean we went through this. What you want to state is this. Alright, let's make sure everything's showing good here. Hey, that's not. Right, so what you want to state is this. Hooke's law states that, and then the same law, you know, the directional proportional law, that the extension, not the length, the extension, I think I moved this thing out too much, of a spring is directly proportional to the load attached or to the force, given that, remember, it had to be within the elastic limit. It is within the limit of proportionality or the elastic limit. That one ain't too bad. So that is 3 marks. So assuming here what the 3 marks is, the 3 marks is you have to state for either force or load, and you need to say extension, not length, and the last mark is for within the limit of proportionality. Alright, so let me look at this table here. So this table here going to, you have to fill this out. I feel this was too bad. I'll lose it there, right. So what you have to do is, I wonder if I could draw this way. Oh, yeah. Alright, but this must put this on Word. What we have to do is calculate the weight of each one. It's 4 marks, so you want to make sure that you use G as 10. The mouse giving a little trouble there. Alright, so we get through there. All you can say, all you feel, boy. Alright, that's now. Alright, so there's what going on here. This is hard. Because all you have to do here is just multiply these by 10. Because it's already in kilograms now, in 9 grams. So this could be 2, 3, 4.2, and you put it to the decimal places. So it's be 2.0, 3.0, 4.2, and 5.0. So the extension here, where you just have to look at the original length. The original length is 70.2. So you just take the length that it have here and you minus the original length. So this is supposed to be 9.0. 83.9 minus 70.2. Let's see what's that. Alright, so that's something around there. 83.9. Put the wrong thing. Minus 70.2. So that's 13.7. And 92.7. Minus 70.2. So that is 22.5. Tell me if I make any mistakes as you go in. So that's the table there. Nothing tough. Me know why. I just put in this slide so the thing go record. What's the sceneries? Everything good, man? Everything good with me. Everything is so good with Spurwin. Spurwin had to change his name. But you know Spurwin is a persona. Alright, so using the grid provided in page 5, I'm gonna zoom this out. Using the grid provided, plotting me plotting that graph, right? Too lazy tonight, but sure once all they get the thing down. Once all they get the thing down there, the graph is a straight line. Spurwin had to change the name to the artist formerly known as Spurwin. If all you know that reference is the artist formerly known as Prince. If all you know who's Prince. Look, let me tell you. Don't mess with a man money. That's what that's what I can tell all you. Alright. So is a straight line. I ain't gonna bother draw it. But they say extension versus force, right? So let me draw the thing there. I am plotting it there, just showing all what the shape looking like. As I say, me feeling to go and dig up no graph paper, image and thing and do it, but I trust in all here. And I tell already last time the graph, when they say x, when they say something versus something, the first something that's going on the y, so the extension had to come here. Although typically when you're drawing a Hooke's law graph, you just draw force versus extension, but then want the thing extension versus force. Alright, so you look here, so extension, and that is in cm, right? So you want to put the unit cm, and the force, let me see how I have it here. I have it as load. Alright, so the load here, this could be, no, I have it as force, so this would be in newtons. You draw your graph, you ting, you draw your line, and you draw your line of best fit. I mean, this is, I don't think that this thing surpassed the elastic limit, but I'm not too sure, but we're gonna assume not. I don't think so. And so basically you get a straight line, and this straight line here, your 8 marks already draw so much graph in all your life already. The 8 marks is labeling the axes, that's 2 marks with the units. The plotting the points is about a little 2-3 marks. Drawing the line of best fit is a mark. Making sure you have the proper scale on both sides, that's a 2 marks. You still put your title and your scale even though that I worth nothing. Hey, watch now. Look, me out to hurt nobody. Me out to insult anybody. The whole team of the last thing was a bootleg knockoff thing. That was the theme of it. So if all you do English, and you learn about metaphors, and you learn about allegories, and you learn about personification and literary devices and thing, that is how it is. But if all you actually Google something called a spoonerism is a parody. You know, you could flip the first consonants of something. So a spoonerism is what it was now. But what you gonna do, boy? That's how it is be. Them things just happen. Alright. So you draw this graph here. Alright, calculate the gradient on page 5. Okay, so I just doing it from the table all. I say I was a lazy man. Alright, so let me look at the table here. Alright, I don't think they specify. I think they say which points to use and thing. So gradient here, there's like a 4 or 5 marks, right? So remember all you draw the triangle and thing. Okay, so remember how to do gradient. Gradient is where slope is y2 minus y1. Now the man get vexed, the man say a bullying all you know. But all you know, that's the persona, that's the joke. You say you get vexed for all you know. Alright, so I just gonna do a basic thing. So I just gonna use these values here. This and 0, I mean, it would be wise for it to use other things. But 22.5, that's the extension, minus 0 over 5.0 minus 0, right? So let me work that out there quick. So that is, by the way, I'm doing this blind, eh? I now get this. As I get, I say let me stream the answers and mess things up now as I go in. Right, so about 4.5, but that will change according to what values you use here. I just pick from the table. As I say, I pull in a lazy man thing here. So you need to put a unit. So unit here is cm per Newton, or cm/n, because it's, remember, it's extension versus force. Now I assume that's a mark. Right, so that's the slope there. Alright, let me look at the next one. Really happening here, boy. Alright. Alright, given the gradient S is equal to 1 over K, calculate the spring constant K. Alright, let me roll there and see what about. But that's easy. This is just maths. There's no physics. But what it's going to do is that this is going to give you in Newton per centimeter, which is, you know, your typical thing. So if S is equal to 1 over K, that means that K is 1 over S. So all you have to do is say 1 over whatever you get. If I would get something a little different from this because I use table values. So 1 over 4.5. Alright, let me see how much is that. So 1 divided by 4.5, that is 0.22. So 0.22. But now you have to put a unit, because unit now not going to be cm per Newton, it's going to be Newton per cm. Okay. That one ain't too bad. I don't notice I switched back to paint, yes. But let me show the work in here. The work in here. Alright. Okay, so again, so you have S is 1 over K. So K is 1 over S. 1 over whatever you get, even if you work on the gradient wrong, you would still get your marks. You would have error carried forward. But as I say, I use table values for the gradient, so I would have something a little different from this. Alright, given that F is equal to KE, calculate the length L when a force of 8 newtons is applied. Yeah. N/cm is correct, Lisa. All they talking about don't be on kicks, all they mustn't be on kicks with people money, you know. Hey, people livelihood and people get on for that, you know. Walk into a man, place a business and tell him something. Nah, man. All they feel it is. Alright. Alright, and I know this looking a little bad. the quality a little bad. But given that F equal KE, calculate the length L when a force of 8 newtons is applied. Okay, so the first thing I want to put is the initial length, right? Because notice they say extension, they say length. So the initial length is we have to check the table for that one, yes? Let me see the table there. So the table, you have to look at the length when it has 0 newtons. That's 70.2 cm, right? So 70.2. Alright, let me come back there. Alright, so 70.2 cm is the initial length. So whatever we get here, we gotta add it to that after. Alright, so when I force a 8, assume that the spring obeys Hooke's law. Okay, so we're gonna say F is equal to KE. And this is going to rearrange as what, boy? We're gonna get the extension, so it's E over F over K. Alright, so F is 8. And K is what we get just now for that calculation. I think I get 0.22. Now, as I said, that value might be different for all because all the gradient might be a little different. Alright, so this is sorry about that seeming a little off, but 36.36. Number 36.4 centimeters. Let me just check something on the table here. As I'm doing this blind earlier. Yeah, I guess that's even correct. And what we need to do is just add that. So 36.4 plus 70.2, 106. Remember again, these answers are a little variable because you know now. Because how it's so dependent on the gradient. Right, I feel like I'll link up this document that I'm doing here after so anybody could check it. Yeah, that's alright, because that's just a mark. Then it is just a mark. But I say it's good to know how you're doing this because you know how that paper won now. Yeah. Alright, so you look at this one now. Alright, so the next part here is just to define some things. Define each of the following terms. So we have moment of a force and center of gravity. This ain't too bad. Alright, that's now I'm just chopping this up. Wait on here, wait. That's now Alright, so we have moment of a force and center of gravity. Pretty basic, but I think it's 3 marks each. I think this question was the thunder question for some of you. Like this question here, I could see why when I was looking at it. I mean, I'm gonna try to work it out and see. Anyway, so the moment of a force, the moment is the product of the force and the perpendicular distance. I think you could get away with just saying distance from the pivot to the fulcrum. You could also define it as a turning force, and so on. So, but you need to have something with force by distance in there now. Center of gravity is the point at which the weight of an object appears to act. I don't think you need to put any more of that. You could also say this is the point at which stability for an object is achieved, or the point at which the object will balance. Something like that. Alright, so let me see there. Alright, so the next one here is state the 2 conditions necessary for a body to be in equilibrium. Okay, so equilibrium in this case means like you have no net force now, no net turning force, no net force or anything like that. So what we want to do there, we want to state, well, first the principle of moments is actually something that you're looking to achieve equilibrium. So state the 2 conditions. So condition 1 is this. Remember, to achieve equilibrium, the anti-clockwise and clockwise moments must be equal, or they must have a net sum of 0. And 2 is that the net force acting on the object must be equal to 0, or you could say all forces must be balanced. Or the sum of all the forces would be 0. Something like that. The point at which the force acts upon the object. If it did say weight, that would be a little better. If it did say weight instead of force, but you still get some marks for it. Nah, don't worry, no. Sometimes it just be a little easy, you know what I mean? It's COVID. Who knows? Alright, look at this one. Alright, I feel there's the question that I mess all up in. Alright, so this one here. This one there, I'm gonna paste it. There's the question here. Well, actually it's not this one. This one easy. It's the one after this. Alright, there's some Figure 2 shown below is a diagram of a non-uniform wooden plank AB, which is 2 meters long. Alright, so I'm gonna say all the mark up all the papers. So there's 2 meters long. First time I'm trying to work it out here, so, and weighs 1,000 newtons, and so that's what we're seeing here. The plank is supported from a ceiling of 2 verticals. So these 2 vertical springs actually going to, since the upward force equal to the downward force, this going to add up to 1,000, right? The plank is attached at a distance of 0.5 meters from each end. Okay, so that means that this is a meter here. I'll put this here. I don't know if that coming important, but C is the center of gravity, okay, and that's the weight of the spring. When the plank is horizontal, this tension in spring P is 600 newtons. Oh well, then this is 400, and that's so show all working. Right. So remember, if this is 600, this one here, the tension of this, the force of this could just be, you know, the difference. So all you have to put here is that the force on Q, or the tension, what is it? Tension. The tension of Q is 1,000 minus 600. That's 400. And I guess they could put something like upward force equals downward force. Something like that, you know. But I mean, it always good, as I say, if you know it, put it. Alright, so this is 400 newtons. I find this moment's question though, the one in Jan was, from what I see, I find that one was tough. And this one here was a little tough. But I find, honestly, the last 3 questions, when I just look at it, it didn't look too tough. But these first 3 was a little thing. Alright, so you look at the others here. Alright, so this one here look like thunder. Alright, so let me take this off here. Alright, this one here look like thunder. By taking moments about A, determine the horizontal distance from P to C. Where P? Oh, P is this. Alright, so let me call this P here. Let me call this D. Let me just call this not D. Let me call it. Let me just call it. Well, let me just call it X and N. Right? So, and this distance here, I don't think we need this distance here since A is the pivot. Alright, so give me a little second here to match this in my head. A is, they say taking moments about A. So we taking A as like the fulcrum. Okay, so we have two moments here, one created by P, one created by Q, and are balanced by the one here created by W. So the distance between P and A is 0.5. The distance between Q and A is 1.5. The distance between W and this is 0.5 plus X. Determine the horizontal, so you have to find X. Well, let me try a thing. Let me try a thing here and see. Alright, so let me get us some names. Let me call this one F1. Let me call this F2. And let me call this one F3. So remember this is 400. Hopefully I get something. Hopefully I get something sensible here. Alright, so let me write that thing here. Alright, so F1 D1. So F1 could be W, right? F1 D1. That weight being balanced by the two springs. F2. Oh, there's a Hooke's law question and this spring question here. The real dread with these springs, boy. Alright, so F1 is 1,000. Alright, so F1 is 1,000. 1,000 times. So D1 is 0.5 plus X. They turn into math, so it's 0.5 plus X, and that is equal to F2. F2 is this spring P, right? So that is 600 times 0.5. If anybody had a bio paper for me, by the way, I'll link that for me, and I could do that one time. But not today, but a day. And 400. So you're looking at F3, this spring here, right? 400. Them real dread to give this question by in these COVID times. Alright, so now I guess it's just to simplify it. So 1,000 times 0.5 is 500. I'm going to sting this here. So that's 500 plus 1,000x. That's going to be equal to 600 by 0.5 is 300. 400 by 1.5 is 600. So that's 900. So 1,000x is 900 minus 500. Right, 2,500 over there. So x going to be equal to 400 over 1,000. I guess that kind of, yeah, that's looking like the thing. I mean, if this is 1 meter, it makes this is like 0.4 and this is like 0.6. Okay, I'm sure everybody get that wrong though. Maybe, you know, put a little formula and thing, try a little thing, you're sure to get some marks. Anybody get our? Me, I feel anybody watching, but as I say, I just doing this for the thing to record. As I doing it. And alright then. Freeform selection. New trace out there. They working wrong. What working wrong there? 300 plus 600. But you know now, that's how it is. Okay. Hey, that question, Eldred. Alright, that's now. Might take in moments. Oh, little 1 mark, 1 mark, 2 mark, and thing does make a difference. Oh, you're working wrong. Okay. Yeah. Anyway, but that the question. I think that is it. It had people's like our principal moments, because it really was red. It really mash up. Mash up as in it mash all up. Alright. So look at the next one there. Yeah, that's a hard one. 2021, born in the wrong time, Ollie. Ollie was born in the wrong year. Alright. I'm going to link up this document I feel after. State why the center of gravity is located closer to the point P than the point Q. Alright. Why is it located closer? Well, because there are more force here. You have a greater force on this spring than this one. And that's so you can reach equilibrium. So what you would say here? So this is due to P having the higher amount of tension. There's only 1 mark, so the distance is reduced to achieve equilibrium, something like that. Once you basically talk about turning forces or achieving equilibrium or something, or you could say also that the turning forces on both sides would be equal or would be balanced, something like that, because this is the rod balancing, something so. Alright. So that's question 2. Alright, let me see question 3. Waves can be described as transverse or longitudinal. Explain what is meant by a transverse wave. Give one example. Well, we went through this in the stream. Alright, so a transverse wave is, okay, define it as this. Alright, so it's a wave that that has its displacement of particles perpendicular to its propagation or its direction. It has crests and troughs. I don't think you need to put anything else more than that. And you know, you could actually draw a little transverse wave in case your writing skills are too good. Me and if you give marks, but at least they'll know that you know. Give one example of a transverse wave. Well, this could be light. Remember that whole thing, light, radio. Richmond and Vegas use expensive gadgets. Light, radio, gamma, microwave, etc. All I go up. I don't realize that I was typing on. Right, so a wave that has its displacement of particles perpendicular to its propagation. It has crests and troughs. May I know what else I could really say there with 3 marks? That's really what it is. And then you have the example. Alright, let me look at this one here. Define the term ultrasound. So while you're saying this one wasn't too hot, well, our ultrasound is a sound wave that exceeds a frequency of 20 kilohertz or 20,000 hertz. Basically, humans can't hear it. It exceeds the normal audible range for a human. State 1 application, ultrasonic needles, clinical imaging of fetuses, something like that. You know, when you're going to see the baby healthy and thing. So it's just one mark. There's him use it for like dentistry, cleaning needles for dentistry, and to clean like jewelry and thing, to scrape up the oxidation. Right. Let me look at the next one. Figure 3 shows the path of a light ray from air through a cube of ice along with 2 rays showing partial reflection. What kind of thing is this, boy? What kind of thing they giving all you here? This thing done looking kind of scary. Determine the angle of incidence on the face MN and the angle of reflection. And then the angle of refraction. Okay, that's so bad. But I mean, if you get that first part wrong, you get the whole thing wrong. Alright, let me give it a whirl. Well, remember, I tell all you, there's always measure, and I'm sure your teacher repeat this umpteen times for you already. There's always measure from the normal. So remember that this whole thing is 90 degrees, right? So this thing here, this could be 90 minus 31. That is 59. So 59 degrees. Right, so 59 degrees is your angle of incidence. And this will actually be the angle down here as well. No, would it? No, it wouldn't. No. Nah, that wouldn't be it here. But that will also be the angle of reflection. Okay, so that is it there. So the two answers is 59. You just have to find the difference. Kavita, sorry, I tell you, this is a sad stream. This is stream to make you cry. This stream only if you don't like yourself. You come in the stream. This stream to mash you up. But don't worry, it's an error carried forward though. So if you get the angle wrong and you have all the working and thing for the other part correct, you should be able to get your marks. Alright, so the answer for this is these two is 59 degrees, right? So this is 59 and this is 59. Calculate the angle of refraction at the face MN given that the refractive index at ice is 1.31. Okay. This one, it's not so bad, it's actually just the diagram look a little intimidating. Anyhow, let me look at it. So the angle of refraction at the face MN. So they're basically asking for this angle here. Well, you just have to do the normal thing. N is equal to sine I over sine R, or sine theta 1 over sine theta 2, Snell's law. And we're going to say sine R is sine I over N. That is sine 59, because that's the angular incidence over what is the refractive index? 1.31. I'm gonna work this out quick. .86. Well, I'm up 0.857. So I can get as close to the thing as possible. 1.31. 1.31. That's 0.65. Right, so we're gonna say sine inverse R. R is going to be equal to sine inverse 0.65. And that is 40.9. Well, 0.87 now, but I'll just point it to 9. Nice, you get correct in here, and okay, that's good. Alright, so hopefully all you get that day. Right, so let's see there, so 40.9. So once again, you just do the formula. Do the formula and work out the thing. It look like a normal question. The only thing that make it difficult is actually the diagram. But once you figure out the diagram, I feel good to go. Alright. Let me check this out here now. On the diagram, on page 11, label the critical angle theta C for ice. This is 1 mark. We didn't work out the critical angle though. Huh. Label the critical angle for ice. Well, it gotta be less than what you're seeing here, because this is total internal reflection happening. Let me just see how much it is though. C will be 1 over N. 1 over 1.31. Let me just work it out and let me just see how much it is. I don't think you have to work it out or anything though. I just checking. The critical angle is about 49.8 degrees. So I don't think you need to use protractor and thing for this, but what you want to do is draw something that like that. Whatever is 49. And label it theta C. I said I see. That's a weird question. Huh, I feel like everybody get it wrong. I feel only just label this one. I wonder if they'll give any mark for that or just labeling the angle, eh? Because really, I mean, it's supposed to be a little less than that. Real chain up thing. Alright. Okay, so that was question 4. This is no. That was question 3. Alright, question 4. Okay. On figure 4, sketch the graph of pressure versus temperature, but it had been Celsius. Remember, if it's in Kelvin, it would look so. If it was in Kelvin, it would look like that, but because it's in Celsius, it will look more so. And this is because, you know, if you was to continue this graph, coming so, it would end up at absolute zero here now, minus 273. So there's pressure and there's temperature in Celsius. You don't have to put in this part here. I just draw it, but it's supposed to be touching kind of in the middle here. Alright, look at this next one. Explain how the graph could be used to derive the Kelvin scale. Alright. You know, this question came a few years ago. Well, you want to say something like this. Since if to convert Celsius to Kelvin, 273 must be added. I guess if you say if the line for the graph is extrapolated or is continued, into the negative end of the y-axis, negative side of the y-axis, the line will touch the x-axis at minus 273 Celsius. I don't think you have to put all that, but I just put in that. I think you just really have to say that 0 Kelvin is the same as minus 273 Celsius. So, right, so like you don't put everything I put here because it's just 2 marks. Alright, so we have a gas laws question here now. A container stores 5 meters. I'm going to put it here. A container stores 5 meters cube of gas at a pressure of 13 atmospheres and a temperature of minus 23 Celsius. Calculate the volume that the same gas would occupy at a temperature of 27. Right? So you have 5, that's the volume, there's the pressure, there's the initial temperature, there's the final temperature, there's the final pressure, the checking for final volume. Right? So you have to use general gas equation. P1 V1 over T1 equals P2 V2 over T2. Alright, so they're going to be equal to put in some numbers here. Pressure 1 is 13, volume 1 is 5, temperature 1, where am I going to convert this to Kelvin? So do we see minus 23 plus 273, minus 23 plus 273. So there's 250, there's 250K. I'll probably remember to do that. And this is, this 300. 300K. 273 plus 20, yeah, okay, so 250. And this is equal to P2, we get a nice number there is 1 over V2, we know that, over T2 is 300. Alright, so all you have to do now is multiply up. 13 times 5 times 300 is equal to 1 times V2 times 250. So basically 250 V2. I'll multiply this up. 13 by 5 by 300 is 19,500. That is equal to 250 V2. So V2 is equal to 19.5 divided by 250. Here we'll get something like a whole number here. I mean, 78 meters cubed. Hopefully I'll look at that. So that makes sense, boy. Let me see. 5 at a temperature minus 23. kind of hard to see if it makes sense with all these numbers here, but 78. I'm just checking back. 13, 5, 250, 1, V2 300, that by this by that by that, that by that by that. Yeah, that is it. Alright, look at this one here. Blocks. Blocks X and Y in figure 5 are identical except for their temperatures. Explain the difference in the motion of the particles in block X compared to block Y. Well, that's easy. Well, since they have a higher temperature, more kinetic energy, and this one are less. So that's what you want to say there. Alright, I'm gonna type that in. Alright, so block X has a higher temperature and thus would have more kinetic energy per molecule, resulting in faster vibration. Something like that. In which direction would thermal energy be transferred? Well, remember, it's always go from higher to lower temperature, so it'll go from X to Y. Right, I'm gonna get this in here. Right, so there's X to Y. I'm gonna just type it. From X to Y. Basically higher to lower temperature. State the condition under which the transfer of thermal energy would cease. Well, that's when they're at equilibrium, right? When the two blocks are the same temperature. That's called thermal equilibrium. Because at that point there, you don't have any net movement energy really, or net transfer heat. You multiply the pressure by 100. Well, if you multiply both pressures by 100, it would cancel off anyway, so you're fine. Not like that's a big deal. Alright, so that is question 4. Alright, let me check 5. Oh, yeah, there's the motor's question. Okay. Figure 6 shows a simple DC motor which consists of a coil of wire ABCD between the poles of a magnet. The dotted line represents an axle about which the coil can turn. The current flows through the coil in the direction shown by the arrows. Draw the magnetic fields between the poles of the magnets on figure 6. Then state the direction in which dA of the coil will move as the current starts. And name the rule. Explain why a split ring is used on a DC motor. Oh, this is bad, you know. This is not to explain the whole thing. Alright. Alright. Oh, they have it south and north here. Okay. Well, it go look so then. North to south, that's the magnetic field. You know, usually it's at the north here. Alright, that's the magnetic field. And Fleming's left hand rule. So you have to use that. So what you want to do is put your use your left hand. Alright, so with your left hand, you're going to put your, I want to know what's the direction on AD, right? So put your index, the index going to be going to the left. Your middle finger going to be going up. So how that moving there? That moving. But how you watching this, boy? You're watching this like going up or going like away from you? But either way, your thumb, if you have your middle finger going kind of into the screen, your thumb will be pointing up. Or your thumb will be pointing towards you, out of the screen. So I think either answer there would work in it because they really say how you're watching this. Alright, so let me. Alright, so need steady direction. It depends on how you're watching it. So which side? DA will, the force on DA will be out of the paper or upwards. I guess if you're viewing it, like from the top, or if you imagine it going in, if you imagine current going into the paper. Name the rule Fleming's left hand rule. Sometimes the two answers here could be correct because I mean people will interpret it in different ways. Nah, it is not a session, Batty Manzel. This is just me recording this thing. And whoever want to come, go come. Because I get the paper now. I'd explain why a split ring commutator is using a DC motor. Well, I told you this already. A split ring is used to enable the motor to keep spinning, or to what we could say, is used to prevent or to break the circuit every half rotation to allow the motor to spin continuously, something like that, or the loop to spin continuously. So it won't go in reverse. So if you say that to that will work. Details. The details is now is not as much as you think. Alright, figure 7 shows a graph of the variation of voltage with time across the output terminal of an AC generator. Calculate the value of the frequency for the generator. Calculate the peak voltage. Then calculate the period of the output. Or state the effect it will have on the period of the output. Oh, this is something different. Okay. Well, if you only look at this here, you can see the peak voltage is 200. Yes, I'm gonna switch this back here. You can see the peak voltage is 200, and the what is asking for? The peak value of the current and the value of the free. Okay. And you can see the period is 0.02 seconds because that's how much is one rotation, right? So to calculate frequency is easy. Frequency is 1 over period. So that is 1 over 0.02, which is 50. Make sure that. Yeah, 50 hertz. So that's the first part. The second part is to calculate let's say the peak voltage applied by the generator across the peak voltage is applied by the generator across a 100 ohm resistor. Calculate the peak value of the current. Okay, so this is just this was the resistance question, right? Okay. Well, this is V equal IR after we do all them circuit and thing. So I is V over R. And you can see the peak voltage is 200 and the resistance is 100. So that is 2 amps. That is all. I'm going to paste that in. Well, I get that. Well, good. That's a good amount of. I find the later questions was easier from when I glanced it. Because when I see that principle of moments thing, I was like, wait, but that question real bad. Right. So let me look at this one here. Alright, so they say the generator is rotated at twice the frequency. State the effect this will have on the period. There's more of a waves question than a generator's question. Alright, so the period at twice the frequency, the period will be halved because you'll have basically half the time per oscillation. And the value of the output voltage. The output voltage would, well, I wouldn't say double, but we could say increase or nearly doubled. I could say double because of the resistor. Alright, and we come into the last one. Alright, so this is the last one here. This radioactivity question. For neutral, okay, radium-226 is radioactive and is represented by the nuclei 226-88 radium. Well, this is easy. State for neutral atoms, state the number of protons be 88. The number of neutrons will be 226 minus 88. and that is 138. And number of electrons could be 88. Easy. Alright, look at the next one. A radium nucleus decays by alpha particle emission. So alpha to a radon nucleus. Explain what is meant by the term radioactivity. 3 marks. Okay, radioactivity occurs when a material spontaneously decays and emits radiation in the form, well, not radiation, it emits particles, emits alpha particles, beta particles, or gamma radiation. You could also put this is just extra. It usually occurs when the nucleus, I can say any nucleus, right? When the nucleus does not have or a 1 proton to 1 neutron ratio. Not always, but at least when it closer. You don't have to put this last part, I believe it did, that's great. But I think they just wanted to like state different types of radiation, the fact that it is spontaneously or randomly emitted, things like that. Alright, let's look at the next one. Complete the equation for the decay of radium 226. So it's alpha, so we want to put the alpha symbol here. 42 helium. We do this exact question that night, but it's the typical alpha question. It comes radon. Right, we have to have a radon nucleus. So 226 minus 4 is 222. 88 minus 2 is 86. So far this radioactivity one is just like real normal. Define the term half-life, normal. Half-life is determined as the time taken for half of a radioactive substance. Or for a radioactive substance, I should say, to decay by half or for its activity to decrease by half, something like that, either one. Okay. At a certain time, okay, so half-life of radium is 1600 years, right? That's what it's saying. Half-life of radium, 1600 years. At a certain time, the sample contains 8 by 10 to the power 8 radium nuclei. Calculate the number of alpha particles emitted by the radium nuclei in the next 4800 years. Okay, so we calculating the number of half-lives, and that will be 4800 over 1600, that's 3. So we're working out for 3 half-lives, and that's 8 by 10 to the power 8, 4 by 10 to the power 8. Right, that's just one half-life, eh? 2 by 10 to the power 8. And the last one will be 1 by 10 to the power 8. So remember this we half-life. What about the number of emitted in the next? Calculate the number of alpha particles emitted by the radium nuclei. Okay, so the number could be, so the number remaining will be this. So the number emitted, basically how much was let out, will just be the difference. I feel like, they probably didn't do that last part. Oh, that's right, that's just a mark. So you gotta find the difference. They're asking how much left, they're asking how much was how much it shoot out now. Alright. I think it had one more after that. Alright, so the last question is, how much more time will elapse before the number of radium nuclei remaining falls to 0.5 by 10 to the power 8? How marks is this? I think it's just about 1 mark. Okay. Well, I think you just have to continue this thing until it reach 0.5. So that'll just be 1 half-life. So it could just be, I don't think you have to show any working or anything. This could be 1 half-life, which is 1600 years. Because after 1 more half-life, it will be 0.5 by 10 to the power 8. This is how much time, or how much more time, right? So it's 1600 years. And it'll be 6400 years total. But they asked that. They asked how much more time, so it's 1600. Yeah, I don't think 90% of people get the moment, so don't worry about that. Otherwise, not a bad. I mean, first half was kinda iffy with our moments question. Hooke's law question was normal, I find. The waves question was okay. What was tricky was the diagram that they give you, but the working I think was real normal. Pressure question was kind of normal if you know what you're doing. Pressure and heat question. Motors question was kind of. I mean, again, if you know what you're doing, it was regular. Radioactivity question was good. It just had like that one tricky part near the end. So as I say, I just putting this up so that whoever like this they could look through this and see the answers. So as I was doing it, though, compile a document with all this working and thing I just put there. So I go put that in the description too. So if you're watching this and you find it a little too hot, and this, when I say if you feel like you get under 70, now that's too hot. So you want to make sure that you get all your marks for your paper 1 or at least 55 out of 60 or something, and you'll be good. So yeah, so that's on Sunday, 1:30. So all you can see the thing there. But that is it for now. I say I wasn't really expecting people to come on here. This is just me recording this thing and I go post. So those of you who are going to see all this Sunday, All right, take care. Until then, and good luck with your exams.